For decades, the Big Boy has towered above all others. It is a 1.2 million pounds legend, famous for its 135,375 pounds of tractive effort and mythic status among rail fans and historians alike. But hidden in the archives is proof of a forgotten locomotive that actually surpassed the Big Boy in raw power, yet it remains all but erased from public memory. If the Big Boy was the unbeatable champion, how could a more powerful engine simply vanish from history? The answer will upend everything you thought you knew about railroad giants. Union Pacific's Big Boy stands as the ultimate symbol of American steam power. Built by the American Locomotive Company between 1941 and 1944, the Big Boy was engineered to conquer the steep grades of the Wasatch Mountains. It stretched over 132 feet and tipped the scales at 1.2 million pounds when coupled to its tender. It was not just size that set it apart, it was raw force. With a tractive effort rated at 135,375 pounds of force, the Big Boy could start and move freight trains weighing more than 4,000 tons up mountain inclines that had humbled lesser engines. The Big Boy's reputation grew far beyond the rails. Union Pacific invested heavily in its legend, turning the locomotive into a household name through posters, model trains, and public excursions. The sheer spectacle of a Big Boy in motion, its 16 drive wheels churning and its exhaust echoing across the plains, captured the imagination of generations. 8 of these giants survive today, and one, number 4014, has thundered back to life in the 21st century, drawing crowds wherever it runs. For rail fans and historians, the Big Boy is the yardstick by which all other steam locomotives are measured. Its numbers, 135,375 pounds of tractive effort and over 6,000 horsepower at the drawbar, became benchmarks in the world of railroading. In every book, every museum, and every conversation about great locomotives, the Big Boy's name rises to the top, an icon of engineering muscle and American ambition. Every legend has its boundaries, and for decades, the Big Boy's numbers seemed untouchable. But railroad archives do not always match public memory. Hidden among test reports, faded blueprints, and factory memos, a different mystery waits. What if the data tells us something the legend never did? What if there is a locomotive whose horsepower and pulling force, on paper and in practice, outclassed even the Big Boy's best days? That idea is not just rumor. It is documented. Factory test curves, dynamometer records, and internal correspondence between engineers point to a rival that surpassed the Big Boy in key measures. The challenge is separating myth from measurement. Numbers in a marketing brochure are one thing. Numbers stamped on an official test sheet are another. To get the truth, the search turns to primary sources. Original builders' reports, performance logs, and the technical journals are where railroad engineers debated which machine truly ruled the rails. The question is not just which locomotive was bigger or louder. The question is which one delivered more power, more consistently, over the toughest stretches of track. If a locomotive really did exist that could eclipse the Big Boy, the proof should be in the raw horsepower curves, in the tonnage logs, and in the first-hand accounts of the crews who ran them. The evidence is out there, scattered across archives and museum vaults, waiting to be pieced together. The only way to settle the question is to follow the trail of numbers and let them speak for themselves. The name that breaks the spell of the Big Boy is the Chesapeake and Ohio H8, better known as the Allegheny. Built by Lima Locomotive Works at the height of American steam ambition, the Allegheny was a machine designed not for headlines, but for the brutal reality of hauling mountains of coal across the steepest grades of the eastern United States. Commissioned by the Chesapeake and Ohio Railway in 1941, The Allegheny was the answer to a challenge that demanded more than sheer size. It demanded unrelenting power, hour after hour, train after train. Lima's engineers, led by William E. Woodard, set out to create a locomotive that could deliver more than just a strong start. They wanted a machine that could keep thousands of tons rolling at speed, even as the rails pitched skyward through the Allegheny Mountains. The result was a locomotive that, on the test stand and in the field, delivered numbers that stunned even seasoned railroaders. Factory records and dynamometer charts confirm it. The Allegheny could produce up to 7,500, sometimes even 7,600 horsepower at the drawbar. That figure stands above any big boy ever measured, not just in theory, but in the hard data recorded by Lima's own test cars and Chesapeake and Ohio performance logs. This was not a fluke or a one-time spike. In repeated tests and regular service, the Allegheny sustained these power levels, pulling trains that stretched for a mile and a half, loaded with over 14,000 tons of coal. The engine itself weighed nearly 778,000 pounds, and with its tender-topped 1.1 million pounds, rivaling the big boy in every dimension that mattered. Yet outside of engineering circles and a handful of museums, the name Allegheny faded, while the big boy became a myth. The numbers are there in black and white. The paradox is real. The most powerful single-steam locomotive in American history was not the one everyone remembers. It was the Allegheny, built by Lima, run by the Chesapeake and Ohio Railway, and proven on the rails of the Appalachian heartland. The story behind those numbers and why they never became legend demands a closer look. Power in steam locomotives is not just a matter of headline horsepower or the biggest machine on the rails. It is a measured contest of engineering, where every number, tractive effort, boiler pressure, cylinder size, tells part of the story. To understand how the Allegheny surpassed the big boy, it is essential to break down what these numbers actually mean. Tractive effort is the force a locomotive can apply to start a train and keep it moving, measured in pounds force. For the Chesapeake and Ohio H8 Allegheny, starting tractive effort ranged from 110,200 to 128,700 pounds force, depending on boiler pressure and adhesion, the grip between steel wheels and rail. By comparison, Big Boy's published figure is 135,375 pounds force, but the real-world difference narrowed in service. The Allegheny's 6 massive driving axles carried over 381,000 pounds, giving it a strong factor of adhesion, crucial for launching heavy coal trains up mountain grades without slipping. Starting power is only part of the equation. Sustained performance depends on how much steam the locomotive can generate and deliver to its cylinders over time. Here, the Allegheny's boiler stands out. With a pressure of 260 pounds per square inch and a firebox area of 135 square feet, it could feed 2 enormous cylinders, each 22.5 inches in diameter with a 33-inch stroke. This combination allowed the Allegheny to produce up to 7,600 horsepower at the drawbar, verified by dynamometer tests, while pulling trains 1.5 miles long at speed. The Big Boy, with its 300 pounds per square inch boiler and slightly larger cylinders, reached about 6,290 horsepower at the drawbar in official tests, topping out just below the Allegheny's sustained output. Adhesion, boiler size, and cylinder dimensions all work together. A locomotive can only use as much power as its wheels can transfer to the rails. Too much force and the wheels spin uselessly. Too little, and the train stalls on the grade. The Allegheny's design struck a balance, spreading its weight over 12 driving wheels and maximizing steam production, so it could keep heavy loads moving where others would falter. These technical choices, recorded in builders' reports and tested on the rails, set expectations for what the Allegheny could accomplish, explaining why, on paper and in practice, it stands apart from the legends. In the early 1940s, the American appetite for coal rose with the demands of World War II. Factories, power plants, and steel mills across the nation depended on a steady flow of Appalachian coal, much of it moving along the Chesapeake and Ohio Railway's mountain lines. The challenge was steep: longer trains, heavier loads, and relentless grades that punished even the strongest engines. C&O needed a locomotive that could do more than just start a heavy train. It had to keep thousands of tons moving, hour after hour, through the Allegheny Mountains without stalling or slipping. William E. Woodard, Lima Locomotive Works' chief engineer, approached the problem with a different philosophy. Instead of chasing the highest tractive effort for dramatic starts, Woodard focused on horsepower, the ability to maintain speed and power over long distances. He insisted that a locomotive's true test was not a single surge of force, but its capacity to deliver continuous output on real mountain rails. His correspondence from 1940 reveals a clear vision. He wrote that the task is not only to start the load, but to move it swiftly and continuously over the mountain, hour after hour. Coal demand, wartime urgency, and operational efficiency all shaped the Allegheny's design. Woodard's team prioritized a massive firebox and boiler capable of generating more steam than any previous engine, and they spread the locomotive's weight across 12 driving wheels for maximum adhesion. Every design decision reflected a single purpose: to meet the era's industrial hunger with unbroken power, turning necessity into engineering ambition. Lima Locomotive Works approached the Allegheny with a philosophy that favored innovation over convention. The H8's 2666 wheel arrangement was a first in American steam, spreading the locomotive's immense weight across 6 driving axles on each engine set and 2 trailing axles to support the firebox. This design was not just for show. It allowed the Allegheny to handle both the sharp curves and crushing grades of the Appalachian route without overwhelming the rails. At the heart of the machine sat the largest firebox ever installed on a reciprocating steam locomotive, covering 135 square feet. This firebox could burn through tons of high volatile bituminous coal every hour, feeding a boiler that turned water into steam at 260 pounds per square inch. Mechanical advances touched every part of the engine. The massive boiler was paired with a mechanical stoker, ensuring a steady flow of coal without exhausting the firemen. Feed water heaters recycled exhaust steam, improving efficiency and keeping the boiler primed for peak output. The cast steel engine bed, a Lima specialty, integrated the cylinders and frame into a single, robust unit, reducing flex and wear during mountain service. Every bolt and bearing reflected William E. Woodard's obsession with sustained power, an engine that could generate over 7,000 horsepower at the drawbar and keep it there for miles. These breakthroughs made the Allegheny more than a brute. It was a masterpiece of applied engineering, built to answer the demands of an era that needed more than just muscle from its machines. C&O crews brought the Allegheny's power to the rails in ways that went far beyond test stands or factory claims. In late 1944, locomotive number 1600 faced a challenge few engines could even attempt: a 160-car freight train loaded with more than 10,600 tons of coal, stretching for more than a mile along the main line between Clifton Forge and Charlottesville, Virginia. The grades were not the steepest on the C&O, but the sheer weight left no margin for error. With engineers and company officials watching from the cab and trackside, Number 1600 started the train from a standstill, its 12 drivers gripping the rail without a hint of slip. On the ruling grade, the Allegheny kept the massive load moving at an average of 15 miles per hour, sometimes pushing to 25 miles per hour on the level stretches. There were no helpers, no drama, just a steady, relentless pull. The dynamometer car logged drawbar horsepower above 6,500, with tractive effort matching the advertised 110,000 pounds force. Veteran engineers later recalled it as almost anticlimactic. The engine simply did what the paperwork promised, mile after mile, car after car, day after day. The logs told the same story. Whether it was a demonstration run or routine service, the Alleghany's numbers were not just theoretical. They played out in real hauls, on real grades, with real tonnage. For the men who ran them, these engines were not legends or marketing stunts. They were tools, powerful, reliable, and proven where it mattered most, out on the main line. By the early 1950s, the Alleghany's power was not enough to secure its future. Chesapeake and Ohio management faced a new reality. Diesel locomotives were rewriting the economics of American railroading. The first wave of EMDF units and Alco road switchers arrived in 1947, and within just a few years, C&O's diesel roster ballooned past 600 units. Diesels ran longer between overhauls, burned less fuel, and needed fewer workers to keep them moving. For every 100,000 revenue ton miles, the numbers showed a clear advantage. Diesels cut fuel costs by nearly a quarter and slashed maintenance labor by more than 15% compared to the H8 class. Beneath the surface, another issue brewed. The Allegany's 6 driving axles bore more than 85,000 pounds each, well above what most C&O bridges and rails were designed to handle. Maintenance memos from the early 1950s document railhead fractures and accelerated track repairs wherever the H8s ran. The cost of upgrading infrastructure to keep up with their weight became hard to justify. By 1956, the last mainline assignments vanished. Most Alleghany's were idled, then scrapped by 1960. In the boardroom, power alone was not enough. The future belonged to lighter, more flexible machines. Union Pacific's approach to publicity was as ambitious as its engineering. The big boy didn't just move freight, it starred in its own story. The railroad's public relations team organized photo specials, inviting journalists and photographers to capture the locomotive in action across the western landscape. Images of the big boy appeared in newspapers, magazines, and even on collectible calendars, turning raw horsepower into a symbol of progress. Model train makers licensed the big boy's likeness, filling toy store shelves and hobby shops with miniature versions that fueled the dreams of young rail fans. Children's books and coloring pages featured the locomotive as a larger-than-life hero, while Union Pacific's own press releases touted the big boy as the mightiest engine on Earth. Special excursions offered the public a chance to ride behind a big boy, cementing its place in popular memory. This relentless promotion ensured that the big boy's reputation grew with every generation, while other giants, built for work rather than show, slipped quietly into the background. Official dynamometer records leave no room for myth. In controlled tests, Union Pacific's Big Boy delivered 6,290 horsepower at the drawbar, a figure confirmed by the Atchison, Topeka, and Santa Fe No. 29 dynamometer car on the Wasatch grades. Yet the Chesapeake and Ohio Allegheny eclipsed that mark, with Lima's own test car logging a sustained 7,398 horsepower at 45 miles per hour for engine number Winx-T01. These numbers, written in ink on factory charts and railroad logs, stand as hard evidence of a power gap that can't be explained away by legend or marketing. Today, the legacy of these giants is measured not just in numbers, but in what remains.
Of these giants,
8 big boys have been preserved across the country, with number 4014 restored to full operation, a living monument that draws crowds from coast to coast. In contrast, only 2 Alleghenies survive, both silent and immobile. Engine number 1501 stands inside the Henry Ford Museum in Michigan, while engine number 1604 rests at the Baltimore and Ohio Railroad Museum in Baltimore. For curators, these engines are more than relics. They are the last physical proof of a contest that played out in steel, steam, and statistics. Today, 8 big boys fill museums, while the Allegheny, once the world's most powerful steam locomotive, survives in obscurity. Legacy is not written by raw numbers, but by the stories we choose to preserve. As digital archives grow, what else slips through the cracks? The machinery we forget reveals as much about us as the legends we remember. What stories are we letting fade today? What stories are we letting fade today?